right. Good morning or good afternoon to all of you. Welcome to the SEG Latin America Regional Advisory Committee's technical webinar series, Recent Advances and the Road Ahead. The SEG Latin America Regional Advisory Committee and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by an extended and answer session. During the question and answer session, if you'd like to ask questions, you can please raise your hand in the webinar interface. And you can also add your questions to the question and answer box. And those questions will be answered in the order that they're received. Today's presenter is Dr. Miguel Bosch. He is an expert in the field of geophysical inversion with focus on advanced seismic inversion methods and data integration in complex reservoir models. He has also worked on inference problems at different Earth scales. On the topic of oil and gas reservoir description, he develops services and technology for upstream oil and gas industry. Miguel has supervised a large number of projects on seismic inversion, reservoir characterization, and integration, as well as developing advanced technology and software for these fields. He graduated with a PhD in geophysics from the Institut de Physique du Globe de Paris, working with Alberto Tarantlo, and was full professor and head of the Applied Physics Department at the Universidad Central de Venezuela. He is an active member of GSH, SEG, AGU, EAGE, IMGE, AAPG, and serves as associate editor in the area of reservoir geophysics for the journal Geophysics. He is the founder and CEO of Info Geosciences Technology and Services. So without further ado, please welcome Dr. Bosch.
Okay, thank you very much, Laurie, for your presentation, and thank everybody coming to the webinar. I'm very happy to make this presentation for the Latin American Regional Advisory Committee of the SEG. So I will be talking today about advanced seismic inversion methods with emphasis on what is on development in the present, what is new, and some interesting view on the future of reservoir characterization and seismic inversion. So what I'm going to present is related to a work I have been doing during a couple of decades, and I've been doing this work in the Central University of Venezuela, where I have been professor in the Applied Physics Department and graduate courses of geophysics, and in my own company, Info Geosciences, during the last 10 years. So we have developed applied work, services, and new technology in the field. The kind of problem I have been working on is related to quantitative integration of the information. So as we want to describe the reservoir as a geological body, we realize that a reliable description of the reservoir has to be done by combining different types of data, different types of information. And to be able to combine all information together, we need to formulate this as an inverse problem. So common inverse problems in the area of seismic inversion commonly relates, for instance, elastic parameters of the reservoir with seismic data. That will be the kind of plain seismic inversion problem. However, seismic inversion methods has been extended recently, so to be taken as a way to integrate different types of information together as a combined inverse problem. So I will be talking in one part of my presentation in the way to formulate inverse problems as an estimation combining different types of data, including rock physics, geostatistics, and well-log data together to estimate reservoir models. Basically, this is involving integrating complex models, which involves different scales, different properties simultaneously represented within the model. Okay, the presentation will have the following topics. I will talk first about advanced elastic seismic inversion, to discuss about the conventional reflection seismic inversion and more advanced ways to formulate it, to then go to rock physics and geostatistical inversion, which involves combining the problem of rock physics model with the seismic inversion itself, and also geostatistical models in order to be able to represent more spatial information and to link and honor well-logged data. As a second topic, I consider that it is very important a change of view on the quality of the seismic inversion for reservoir characterization, in particular related with the application of elastic full waveform inversion instead of conventional reflection seismic inversion. So I will be talking about this topic as well. And finally, I will be talking about more complex and challenging problems which involve sort of a full multi-physics inversion regarding reservoirs, and also automatic inversion to speed up the model building of reservoirs. Okay, I will include in these different topics, as you see, they are kind of three important topics. I will be including the needed theory and technological discussion along the way we go. So we will be starting from more simple to more complex along these topics I'm showing here. Well, we have been working in developing advanced seismic inversion based on reflectivity. And this involves combining additional information apart from the seismic itself, which involves modeling the wavelets. So taking into account the wavelet variation, because wavelets are not stationary or completely exactly along all the surveys. As you know, wavelet can change. And an important issue is to be able to include within the inversion some wavelet variation. In our model, we included. And also, we are taking into account in this kind of inversion, the statistical information about the correlations of the properties vertically, and later I will show also laterally. So in our model of advanced seismic inversion, you will see at the bottom of this slide the objective function. And this objective function, as you see, will have three terms. One term is related with the seismic likelihood function, seismic misfit, so to fit observed with calculated data. The second term is related with the prior information, including geostatistics, and the last term is involving the term corresponding to the source wavelet. So allowing some adaptation and inference of the source wavelet from CDP to CDP. Our formulation has been applied in several areas and many projects. I will show you as example here one case, which is in Los Llanos Basin of Colombia. This is in particular in Rubiales Field. And this is an application I worked on about 6 years ago. Rubiales Field is one of the most prolific llanos fields of Colombia, and it needs to be exploited using horizontal wells. The basal sands of this area are very complex, and the target and the idea there was to be able to describe in 3D accurately the morphology of these sand bodies. Okay, this is an example of results of the simultaneous inversion, density, P wave velocity, and S velocity for this area in the 3D volume. And in this area in particular, we were able to further characterize as a second step the lithology very accurately with a sand estimator. and the oil-bearing sands. And this was done in this case by correlation, correlating elastic properties estimated by the inversion with the corresponding reservoir parameters we are interested on, in this case, the sun estimator and the oil indicator. The models here were very robust, and particularly the density in this technology is very well defined, or very well resolved by the inversion. And so we had in this area a very good correlation with the lithology as well. So we were able to create a very accurate 3D description of the sand distribution. In this case, I can show you in this figure that you see at your right-hand side, the resulting sand indicator, which you can see in red colors and yellow, which are the sand content. So the opposite of the shale fraction. So it's actually shale fraction. In blue, you will see the shale, and in red, the sands. And together you can see superposed the corresponding V shale of obtained with a well log in the area. In this area, a correlation of 80% with well logs was obtained for this kind of indicator for the sand. And at the bottom, there is a nearby area with a similar method applied. And these 3D obtained models for the reservoir parameters, in particular the lithology, were actively used by the client during many years to design and to drive the drilling of the horizontal wells. So in the figure, you can see one of the horizontal wells landing to the sand body. And this area was extensively exploited using approximately 400 wells a year. So more than 1,000 wells were developed with the base of this kind of development. This is, in this figure, a presentation of a time slice through the V-shale model, where you can see the heterogeneity of the basal sand. So that is what I was mentioning. So these sand bodies are very heterogeneous in this area, and for this reason, the inversion and estimation of the lithology was so important. And kind of after 1 or 2 kilometers, we can see in this correlation plot, indicates that after more than 1 or 2 kilometers, then we have actually an independence of the sand bodies. Finally, this is also combined with well data to obtain a 3D model that actually fits both the seismic and the well data. So this process is more or less what is a standard in the industry. Okay, but take a look now on something more advanced, which is called the rock physics seismic inversion. So in this case, we are going to use two types of modelings together jointly, not only the seismic modeling that you can see at your right-hand side, but also a rock physics model. And within the model, simultaneously, we are going to have not only the elastic parameters, but as well reservoir parameters, which can be, I'm going to show an example, V-shale, total porosity, and fluid saturation. We can have also lithology categories instead of a continuous indicator like V-shale, right? So we have two layers of parameters, a hierarchical organization. First, we have the reservoir layer of parameters in the sense of describing the reservoir, and then the elastic part of the model, all described together. So the rock physics model is linking the reservoir set of parameters with the elastic set of parameters. And the seismic modeling is linking then the elastic set of parameters with the observed data, which in this case are angle gathers. So by inverting jointly this set of this network of inference, then we can jointly estimate elastic parameters together with the reservoir parameters. This problem, we have solved it in two ways. The deterministic manner, which involves obtaining some gradients and approximated Hessians and iterating towards a maximum of the posterior probability, so an optimal model. And also we have solved it using sampling approach, which means that we generate a large number of realizations, from this large number of realizations, then we can estimate a probability density distribution. At the bottom line of this slide, you will see the posterior probability that describes this complex problem and involves several terms. I will talk later about how to construct these posterior probability densities. Okay, I will show in this case the solution with Monte Carlo. The area example that I'm going to show at the moment is in a gas field. So we have some gas-bearing sands. There is some description at your right about the gas indicator previously created in the conventional manner, and some indication at your left-hand side about the reflectivity. So this is a classical type 2 AVO where you have strong reflectivity. At the bottom, negative reflectivity at the top of the reservoir, and positive reflectivity at the base of the reservoir, and a significant AVO effect. So the Monte Carlo approach or sampling approach will go through the reservoir parameters and the elastic parameters to the data, to the seismic data. This animation is showing this process. So we have in this figure 3 columns, and these first 3 columns correspond to reservoir parameters: porosity, V shale, and water saturation. The 4th, 5th, and 6th column correspond to VPVS and density. Each of the lines correspond to a different location. So I'm showing 4 locations that correspond to a known well for comparison. So the process of sampling is as follows. We have a prior probability distribution, and we have a generator of realizations of porosity, V shale, and water saturation. Using the rock physics model, which by the way was calibrated to the area and used a combination of Gassman model together with a critical porosity model, then we generate VPVS and density. You will see, for example, that when we have important gas presence here, realizations are in the green curves, then we have a smaller density. We have also a smaller VP. Because of the rock physics model. Then, given VPVS and density, the full gather is calculated and compared with the observed gather. We have here, as I mentioned, 4 locations, 4 wells, and we observe the typical AV2 response, which we can see at the top of the reservoir, an important negative reflection, which increases with the angle. And then we have at the bottom also an important negative reflection that increases with the angle. At short offsets, these amplitudes are smaller. This is a class 2 AVO. So applying the sampling and the Metropolis method, the simulated data is compared with the observed data, and the models that appropriately fit the observed data are retained in the chain. You will see here that most of the retained models for the 3 first lines, 3 first wells, are representing or showing a large frequency of gas presence in the realizations, whereas at the bottom one, which is a dry well, we have very few gas presence sampled. This exercise, this project was developed not only to indicate where the gas, if the gas was present or not, it was developed to be able to estimate the water saturation, so the gas saturation, and was implemented in this area with eight wells are present. So once calibrated in the wells, was extended to the complete area. Well, instead, this runs about 10,000 realizations, and the realizations allow to build up posterior probability densities. As I'm showing here, for instance, only for the saturation, which was the parameter most interesting in this case. And we have that distribution of saturation. This is the cumulative probability density. The black line is the median for a gas bearing well. This is the average seismic response calculated, and then we have the observed gathered at this location. In the bottom, we have an example of a dry well, where we don't see the typical red-blue response of the seismic, and of course, the method also indicates correctly that we have a very large water saturation, very small probability for having gas here. These plots correspond to the 8 wells in the area, and I'm representing or showing also in the plots with a magenta line, which is this kind of line I'm showing with the cursor now, what the petrophysicist result from well log data is, and what the estimation from the rock physics seismic inversion was obtained for this well. You can see a very good correlation. We have a small time shift here, but this is not a matter of the inversion. This is just, sorry, just a matter of the time fit. And so on for different cases, like in this case, sorry, where we have then the case of dry well. Well, this is the example of rock physics inversion. And let's do now an additional step in complexity. Remember that in the rock physics seismic inversion, we have added the rock physics model. We are going to have to add now, or to consider now, conditioning the properties, the reservoir and elastic properties to well log data in a specific location. So adding information on these well data at the given well locations. Okay, in order to include within the model the parameters related with the well log data, there is an interesting issue to consider, and the issue is that we have two different scales. We have two different scales because the seismic data has a given resolution, and the well log data have a different resolution, you know, a finer resolution. So to some point, or we need necessarily to include in the model both scales. So we have some properties that need to be represented at the scale of high resolution, and some other properties, or the same properties at low resolution, like the elastic properties. No? So we are going to have here this interface here between properties at high resolution and properties at low resolution. The relationship between them is given by a change of scale transformation. In the case, or in this case, we are using Backus transform, which is the standard. So this is going to be the function that allows to link the two model parameters at different scales. So the reservoir parameters will be described at the high resolution scale. So we have solved this problem as well, both in sampling and in the deterministic approach. The combined probability densities at the bottom. I will talk later on these issues. And this is a typical result in a section corresponding to a gas field, we can see the water saturation resulting from the inversion and the gas bearing layer, which is, I'm indicating it with a cursor. So in this plot, I'm showing 9 components of the plots. What do they mean? So the left-hand side column is the inversion in which the geostatistical rock physics inversion in which we are going to eliminate the influence of the seismic data. We can do this by assigning to the seismic data a very large uncertainty, for instance. So all the weight in the inference will be on the side of the geostatistical model. By the way, here we have 2 wells, well 1 and well 2. Well 1 will be the conditional well, is the conditioning well. We cannot see it here because the data really fit, the result really fits with the well. And well 2 is the blind test well to compare the results. So applying the geostatistical component, what we have as result for elastic and porosity parameters, reservoir parameters, I'm showing here porosity and acoustic impedance, water saturation, is a geostatistical extrapolation of well 1 along the horizons towards well 2. This is the geostatistical or pure geostatistical inference, which will be equivalent to a kriging result. In the middle column, I'm showing the opposite case. I'm going to eliminate the influence of the geostatistics on the joint inversion and only make a seismic inversion, still on the conditioning, including a rock physics model. So we can estimate acoustic impedance, total porosity, water saturation. But in this case, you see now the texture and the information of the seismic data coming up, of course, at the resolution of the seismic data. Finally, in the third column, you will see the actual joint geostatistical inversion, where you can where the 2 types of data and information are combined. So this is the final result, the combined result, where you can see the result of the inversion with a very fine layering, which is imposed by the geostatistical model and the fine layering of well 1, and also the information provided by the seismic. Well, when we compare the results in the blind test, which is the test W2 here, we can see that all correlations improve in the combined geostatistical and seismic inversion. So as much information we combine, and this is very logic, then seems very natural, then we have a better estimation, a better inference. So here I'm showing that the inversion and inversion algorithms are taken into account within complex models that involve rock physics or geostatistics are a very good tool in quantitative integration of information for the reservoir. Well, I plan to switch now to a different topic that I mentioned to you regarding what is coming up in reservoir description and seismic inversion. I just talked about combining information, how one line of improvement is integrating more information with inversion. I'm going to talk now about the quality of the inversion itself. At the industry level, we have been using on regular basis reflection seismic inversion. That means Sopritz equations. We calculate convolution with the reflectivity to model the seismic data. The seismic data in this case has to be migrated. And this works CDP by CDP. This has been a very useful tool. This allows to obtain very important information. However, there are limitations on this method, on reflectivity seismic inversion. And the limitations are that mostly the information is obtained from from the reflectivity, from PP reflectivity of the compressional waves. But it's not including or not accounting what corresponds to different types of phases, like PS or P2S conversions can be included, but it's not very easy to include them. And also are not including other phenomena like multiples, surface waves, diffractions, channel waves, diving waves, etc. On the other hand, if we are able to model all these phenomenology of the waves together by solving the elastodynamic equations, for instance, solving it with finite difference or solving it in the frequency domain, so we can set up the inversion in the setting through the method of full waveform inversion. So with full waveform inversion has the advantage of explaining the complete phenomenology of the wave propagation. This is one advantage. Okay, the second advantage is that when we are using reflection seismic inversion, we need to have the data migrated. So we are relying in a very long processing, seismic processing. And then the inversion step is inheriting or carries on the different errors in processing. So sometimes it's frustrating because sometimes the reflection amplitudes has not been correctly preserved, or different issues on noise are already present, or different problems in the processing are there. So the results that we can obtain after the seismic inversion have already the fingerprint of this previous seismic processing, in particular migration. If we have done the correct migration, the correct velocity migration, etc. However, in full waveform inversion, we work directly with the shot gathers, and the processing is very simple. So definitively, elastic full waveform inversion is the future way to exploit seismic inversion for reservoir. However, it has some problems. Some problems are related with the amount of calculations needed. I'm going to talk a bit on the work I have been related in this field about from 5 years ago of developments that involve full waveform inversion at 2 scales, in which one scale is for inversion and parameters, a finer scale is for the seismic modeling. We have developed the 2 methods, the method based on gradient iterations, which is the most commonly used. Also the method based on the Hessian calculation, which is more time consuming, but more precise. In my right-hand side, I'm showing a checkboard test for joint estimations of VP, VS, and density. This is a couple of 1 or 2 iterations for a Hessian-based modeling based elastic inversion. And you can see that it's very completely solved, but problems of crosstalking almost has all been resolved. So the elastic inversion, or the wave, the seismic data obtained contains all the information needed for decoupling and estimating VP, VS, and density, or any other combination of elastic parameters. Well, there's been different approaches to try to accommodate the problem of elastic full waveform inversion to reservoirs, because when treated as a complete problem, as a global inversion problem in the complete area, it is very consuming in computational resources, have some limitations then on the frequencies that we can reach, and we need for reservoir description, particular fine frequencies. So I've been involved in the recently in research on what is called focused intensity seismic inversion. The basic idea is to reconstruct the source, or reconstruct the data, pre-process the data taking into account the conventional point-wise collected data to build up macro sources or multi-point data using the superposition principle. Of course, this kind of focused intensity data could be hypothetically collected in the field, but it is not necessary, and it would be too complicated. In the left-hand plot, I'm showing here one type of wavefront, which can be a convergent wavefront. So supposing we can calculate appropriate time delays, it's possible using several sources to generate a waveform that is going to converge to a focal point, and this focal point can be located in the area of the reservoir in which we have interest. So in this case, this is a data-driven approach to, the idea is not to estimate or to infer the elastic properties in the complete volume, but to make an emphasis on a specific area, and for this purpose to use intensity focusing energy. And this is the integral of the kinetic energy due to this kind of convergent wavefront. Okay? We can call this the action. The action is the integral of the energy in time. So we can see that we could select a specific area and produce a convergent wavefront that has or concentrates the action in a specific region. This is the modeling of such kind of convergent wavefronts. So at different time steps, as you can see here. Here I'm showing different distributions of this action for a point source. For instance, that would be the middle line would be point sources. And here I'm showing for the convergence source. So we can see that the convergence source is able to concentrate the energy, whereas the point source has a lot of problem in penetration. Another method is based on superposing beams. In the same manner, beams or seismic beams can be constructed by combination of different shots with appropriate time delays and sources to generate beams. At the right-hand side, you can see a beam. So a beam will have some thickness and will be calculated with different, with the correct travel times in order to keep approximately planar front. So this beam also has designed or is designed to go to a focal point, and we can also select the inclination angle. So by combining several beams, we can also have accumulated energy, accumulated intensity in some specific area. So it turns out that when we do full waveform inversion in this manner, with this preparation of the data, which is called focused elastic seismic inversion, we are interested in a given area, not in the complete volume, a given region of the volume. Then this data has more sensitivity. The parameters, the elastic parameters of this focused region will have more sensitivity to the actual data than the regions to the sides. So these are results of inversion in a Marmouzy type model for BPBS and density. This is a salt layer in Marmouzy model that is correctly solved by the elastic full waveform inversion here, just to show that this is a good resolution of the three parameters simultaneously. And it turns that using conventional point-wise full waveform inversion, in which we consider the complete set of shots, but without constructing this kind of focused seismic data, we have a slower convergence. This is the normalized model misfit, whereas when we use the beam focused seismic data or convergence focused seismic data, which is the 5 and 4, we have a much improved estimation and faster convergence. Okay, There are different ways. This is not the only way in which target-oriented full waveform inversion has been worked on. Okay, full waveform inversion, however, has been worked a lot in the acoustic model, but the elastic model is a challenge, and this is research in the direction to be able to use full waveform inversion in the elastic model to characterize the reservoirs. I will go to a third topic. First, I'm just making some summary of this topic of the elastic full waveform inversion and benefits. These are projects that I have in development, progressive development, and I'm going to talk in the moment about these two other challenging topics. Not only which has interest in different companies at the moment, different research groups. This is also part of the idea of combining different types of information together in a quantitative way. So the goal of the full static reservoir project, and this is more or less only showing kind of a development stage, is combining different types of geophysical data together and all the information that is related with the reservoir together in order to estimate the reservoir properties. In this case, this also may involve additional data, not only seismic data, could be also gravity data, control source electromagnetic data, together in the same inversion scheme. What is the goal behind these efforts? Okay, all of you that have worked in reservoir description knows that the time process involving from the acquisition of the data, processing of the data, starting to characterize the well log data, going to make seismic inversions, then we have a group that makes or a specialist that make the integration, then this goes to a different kind of group that will do the static model and the fluid flow model. So the complete process to build up a complete reservoir and reliable reservoir model takes about 1-2 years. The idea is to be able to shorten this period so that the period of elaborating a reservoir could be much shorter, like say 3-6 months. So there is an effort in this direction. Obviously, the problem of the long period of 1-2 years is because everything is done by separate contractors, by separate softwares. One of the contractors or one of the specialists then give the report to another one. And in all this, there is a lot of information that is lost. And in particular, uncertainties are almost impossible to be traced from one process to the other. However, if we place everything as a combined inference problem, we have the opportunity to really solve this problem much better, quantitatively integrated, trace the uncertainties, and as well in a shorter time. So how to formulate such kind of complex inference problems? Well, we have, as I said, different types of information, seismic, well logs, sometimes oil production data, rock physics, etc. I will talk to you a little bit about the theory very briefly, because this is related with what is called Bayesian networks. So it's a methodology to be able to make inference in complex models where we can describe parameters for different components and their specific relations. Say, this part of the model could be the parameter describing the porosity, this other part could be describing the permeability. I'm showing in gray boxes subsets of the parameters. And I'm describing in white boxes the data, the observations. This could be well log, this could be oil production data, seismic, etc. And in the arrows are represented the relations the relations we can model between these parameters and data. For instance, this arrow could be a rock physics model, or this could be a flow model. And then to link with the data, this could be gravity model. It depends on the type of data. So the whole set that relates the causal relations, the components of the parameter with the pointing causal relationships is called a direct acyclic graph. So in the direct acyclic graph, if we are able to describe probabilities and conditional probabilities associated to each of the relationships, prior probabilities related to each of the parent nodes. Parent nodes are the nodes that are not conditioned by another nodes. Likelihood functions, which are related with the fully descendant nodes, which are the data. We configure what is called a knowledge network or a Bayesian network. These kind of networks, by the way, are not used only in geosciences. This is kind of imported to geosciences, or well, applied in many fields. And this is the basis of a big part of artificial intelligence algorithm. In particular, the algorithms that recognize language are based on Bayesian networks, though not distributed in space, but distributed in time. In here, we are formulating the problem by its nature is described in space and will be in time if we see then the dynamic reservoir later on. So, well, I'm just writing very briefly. There's a way to obtain the combined probability density. Every internal link is producing a conditional density and so on. These are likelihood functions. So each of these arrows can be modeled either numerically, as when we do seismic modeling numerically, could be modeled statistically, like for relating rock physics parameters, or geostatistically. So this is the forward direction of the network, these white boxes. And then we have the inverse relation, the inverse direction. So in the inverse direction, we use different we can use different types of algorithms. Could be optimization, which is well calculating the gradient, the Hessian, iterating. You know, in optimization, we start from a given point and we do several iterations to the maximum. We can use neural networks, which basically is also an inference method in which is only one iteration that is done, but it requires previous training of the network. Or we can use sampling, Monte Carlo, what I already talked about, which is based on obtaining many samples instead of the optimal one. So we can go forward in the network from parent parameters to the data, or backwards in the inverse sense. Okay, so forward, backwards. And in this way, we can solve the complete inverse problem. The inverse problem can be solved by patches, so we can do an optimization of a group of processes, or we can do it in the individually as well, by first doing the seismic inversion, then going to the rock physics inversion, and so on. But if we repeat the process forward and backwards several times, we converge to some optimal solution, or we can do a complete sampling of the solution. So that's the idea for attacking these kind of problems of the full static reservoir. This would be a kind of graph for this kind of problem, which is very similar to the one I showed for the rock physics inversion, but has also, in this case, reflectivity density. Well, I'm just about to finish, but the last topic is the second aspect of this modeling, which is considering what happens if we want to model the evolution of the reservoir during production. So we have the project that is called full dynamic reservoir, which involves linking the variables in time. So this will be the knowledge network associated with this kind of problem. We will have a static part of the model, which is lithology, porosity, permeability. And we will have the dynamic part of the model, which can be variable pressures, variable saturations, which links the dynamic and the static model is the fluid flow modeling, okay? We may have also seismic data and time-lapse data at different stages of the process, conditioning these dynamic variables. So the same objective, all the information can be quantitatively integrated in this manner through the knowledge networks, and then coming up with a model that quantitatively fits all the information and where the uncertainties can be well traced, okay? And well, the different components of the problem are solved together instead of separate in a separate manner. Well, this is kind of more, remember that this talk is called present and future. So this is more on the future part, but likely to be not so far from now, right? There is a lot of interest in this kind of automatic processes. Okay, I will say that apart from the quantitative integration, there's the issue of that many of the calibrations that are related with all this process, like estimating the waveform or calibrating the rock physics model, etc., can be automated or should be automated in order if we want this to run in a short time. This will not pretend to be a substitution of the knowledge of the specialist, because this can be this needs to be supervised by the specialist, but this is just a better tool to integrate for the specialist and to be able to obtain results in a shorter time. Well, I'm finishing now with the talk, and I have to acknowledge for results I've been showing this presentation, some of our clients, Pacific Rubiales, Ecopetrol, Suelo Petrol, in specific for some of the data and shown. More information on these topics can be found in these papers. This is a paper in the Encyclopedia of Exploration Geophysics. This is an online encyclopedia of the SCG, completely open source, about the integration of seismic rock physics, spatial models, in reservoir geophysics. And this is a book of the AGU about inference in complex models, a little bit more theoretical on these Bayesian networks. Well, thank you very much.
All right, thank you. If you have a question to ask, you can raise your hand in the webinar interface, or you could add your question to the question and answer box. We have a couple questions already. In terms of seismic inversion, what are the limitations of the Bacchus upscaling?
Okay. Well, there are limitations on Bacchus upscaling, because Bacchus upscaling is almost for near vertical incidence, right? So there are already models to generalize Bacchus upscaling. However, in most of the problems for seismic reflectivity, the Bacchus upscaling works very fine, very well. In addition, if we go back to this part of the method, let me go back a little bit. It's a good question. In fact, we have here the change of scale, and the Bacchus upscaling will be here. It's possible to add an uncertainty on Bacchus upscaling this method, so that it may not be in the way we have solved it. We have used it as an exact transform, but also this can be a conditional probability density with some deviations to account for these possible approximations of the Bacchus upscaling.
Okay, thank you. There's another question that's a three-part question.
Mm-hmm.
The person has three general broad questions. The first one, how do you handle regularization issues? And two, how can you tell us how how it was to work with Alberts. And 3, comments, suggestions for students given current reality in oil and gas industry and the world. Thank you very much.
Okay, can you repeat me the first one, Laurie, please?
Sure, yeah. The first question is, how do you handle regularization issues?
Okay, yes. Okay, for the first question about regularization issues. When we describe the prior information on, say, this set of reservoir parameters, there is a prior information to include, that is here in this blue ellipse. So this prior information comes into the corresponding prior probability density, which is this one. And this can be modeled through a covariance matrix. So this covariance estimated in this formulation will be describing correlations across, say, V-shale and porosity, or a semi-variogram. What is the variance? So this is the natural way, this is a natural approach, the geostatistics of regularization. So this would be kind of having the same effect than other ways to regularize, like Tikhonov is very well known, and there are many others. But I like this one based on geostatistics because it can be characterized from data. Well, the second point was how was to work with Albert. I passed very good time with him. He was an incredible person, very creative, and really led the researchers, in my case, I made a PhD, but I came to his lab having a research experience because I was previously a professor instructor at the Central University and made some previous research. And he liked it to give a lot of independence in the development of the work and contribute in the essential issues. He was a great scientist. I appreciate him very much, and everybody knows all that he created in inverse problem formulations and seismic full waveform inversion. Right. And finally, the third topic.
Yep. Do you have any comments, suggestions for students given current reality in the oil and gas industry and the world in general?
Well, these methodologies that we are studying in geophysics have a lot of applications. I've been able to share with professionals in different fields, and geophysics is evolving. There is a lot to do in different types of energy, geothermal, environmental. This may have connection also with climate modeling. And there's an area of how geophysics can help to be integrated into intelligent cities, for instance. And of course, the oil sector, which will be necessary for some long time, although we understand that different types of energy are needed to progressively have more proportions of the energy usage in the planet. So there's a lot to apply.
Okay, great, thank you. Our next question: how many takes? How many takes do you need for a static model once the 1D rock physics models are already done and calibrated? So how many runs, I guess?
Well, it will be highly specific on the case and on the complexity of the reservoir. But nowadays, my feeling is that even the complexity of these models, we have every day an increase of computational capacity of the processors, of the memory, of the systems, and that this runs very, very fast. So it's not a great worry. In fact, and I believe that all these elaborated and complex relationships can be fully quantitatively modeled and treated.
Okay. Next question, it deals with slide 15. The question is, I believe it is slide 15, geostatistical and rock physics, seismic inversion condition to wells.
All right, yeah.
It wasn't really.
This one.
Yeah, I think he's asking, are those conditioned to the wells?
Are those, sorry, Lauren?
The rock physics and seismic inversion, are they conditioned to wells or?
Yes, they are conditioned to the wells. Yes, both the elastic and the reservoir parameters. So if we see in the example, the well one is the one conditioning. You cannot see it almost here because it's fully. We demanded here a full correlation, so no nugget effect. So it's almost the result is almost tied to the well. Here in the seismic inversion, you can see the location of the well one because here we eliminated the geostatistical conditioning. So here is the well one. And so you can see that both in acoustic impedance in this case and porosity, it fits and is conditioned in both fields.
Okay. Next question. What is the maximum depth for fluid velocities / saturations? Do they perform for 4D CSEM?
Yes. Well, this is a variable according to the area, according to the rock that is containing the gas. Of course, as we go deeper, it's more difficult, but depending on the thickness and depending on the porosity, it's possible to use, a standard fluid substitution to see, to check. Okay, in the example I just showed, it was rather deep gas-bearing sand. Sorry, I believe it was a kind of 3 kilometers, but it was a thick sand, and it was very clear that has the fluid has seismic sensitivity, right? So it depends on the porosity, on the several factors, the thickness, etc.
Okay, we have a follow-up question to that. To add on slide 15, the water saturation is the number on the bottom percent of water saturation, 99% to 40.
Correlation, these are correlations to the well.
Okay, all right.
It means that we have a better 94% in the geostatistical and seismic combined approach.
All right. And so that's geostatistical extrapolation from well 1 to well 2?
Well, it's just a kind of kriging. So we have poor here, and there's the correlation range. So as we get far away, we start losing the correlation because that's the way it's been described here with its characteristic correlation lengths. There's also an issue here, for instance, to notice. This is a shale. We have a shale here that is the seal of the gas reservoir, and in the well, if you follow my mouse cursor, you can see this red dot. This is the top of the reservoir, and this is a seal. So, but this is the seal, and this is a shale. So this is a shale layer sealing the reservoir. But it has a large porosity, this shale. So this problem, the seismic alone cannot solve it, all right? But when it's conditioned with a well, you can see that the problem is actually solved. So the shale, in this case, corresponds to larger porosity, is currently estimated where it should be according to the well, and then the gas layer it goes below. Now you cannot see it because, okay, it's a different plot, but I know the case. So the gas layer is just below the shale here. So in the seismic alone, this wouldn't be resolved properly because of the crosstalk between elastic parameters.
Okay. Well, we have lots of questions. The next one, how do you see the application of seismic inversion methods for engineering issues, considering that there are not many ground truth data available? The medium is normally unconsolidated and the source frequency are quite high comparing to exploration seismic.
Well, I have not worked directly in the engineering applications, but I have seen different work in environmental area, combining seismic and electromagnetics. I think these methods are promising and could be used. Now it comes the viability and cost of having a net of geophones and so on. But as the geophones can be placed now more easily without cables, and it's likely that can be interesting to apply it to an engineering level. If we go much to a much smaller scale, there are the non-destructive tests where sonic waveforms are used to even describe if you have fractures within some pieces of metals and mechanical parts. So there are different scales in which these elastic and acoustic methods can be employed.
Okay. How do you handle the very shallow, less than 300 meters, and the deep, greater than 3,000 meters reservoirs?
Well, very shallow, I don't see that there is a major problem in imaging in itself. The only issue is that sometimes the rocks are not consolidated. But if you use the appropriate rock physics model, that means a rock physics model for non-consolidated rocks, that should work well. And then the deeper, well, that depends on penetration of the signal. And I believe can be also are also useful. I've seen seismic inversion in deep areas, and it's useful. In particular, if you are able to trace uncertainties, then you can check on how much of the data, how is your information providing, how is your data providing information on the parameters.
Okay. What is the difference in resolution for pre-stack inversion and full waveform inversion?
Okay. In current applications, it depends much on the example. Here in my examples, there is a big difference because we are doing this still in development and in sort of not high power computational clusters, but in a reasonable local cluster. But in principle, there is no there is no limit if enough computational power is used. The thing is the cost, and in common elastic applications. So elastic full waveform inversion has not reached the point to be used in a standard manner in reservoir characterization yet. It's in this research and development stage, but the frequency will be reached further on.
All right, we have time for a few more questions. why do you include permeability in the static model section when there's a relative permeability effect depending on the relative percentage of permeability and the type, gas, oil, heavy oil, etc., for fluid flowing in the reservoir?
Okay. Well, so some parameters here are represented in dynamic part. They have some component that could be static and some part that could be dynamic, some delta parameter that could be part of the variability. So the reason in this specific graph, I put it here, is because this graph was oriented to justify an inversion of the permeability from the time-lapse data and the production history data. So it was on the scope that if you have an initial model of permeability and you invert through this model, then you get some sort of estimated permeability that is able to explain the production history data and the seismic data. Okay, of course, the models can be complemented or made more precise if we include some additional variation of the permeability with time, which can happen if porosity changes or different processes.
Okay, we have a couple more. In the full dynamic model, how can you be assured that the 3D permeability model is reliable? Do you previously evaluate it using a fluid substitution model?
Okay, can you read me again the question, Laurie?
Sure,
Please.
yes. In the full dynamic model, how can you be assured that the 3D permeability model is reliable? Do you previously evaluate it using a fluid substitution model?
Okay. Yes, I think my later comment will explain this one as well. This graph is done with the idea that with the time-lapse seismic data and production history, an initial permeability model will be, when we turn these white arrows in the opposite inverse direction, will be estimated, the permeability, so will be adapted. And then we may do this forward, backward several times to have the best permeability.
Okay.
And additional comments. These graphs are a bit able to be modified according to the relevance on the issues. For instance, I've been showing isotropic here, but if one thinks that anisotropic is relevant in an area, then we can add to the knowledge network the corresponding anisotropy and start relating it. And so it's kind of pertinent to what we want to do with the inference network.
Okay. Are CSEM data and mass model, are they considered as constraints on the full waveform version where property models are also updated? I'm not sure exactly what they're trying to get at.
Yeah, if you can please read it again.
Sure. CSEM data and mass model are considered as constraints in the full waveform inversion, or property models are also updated?
Okay, in this graph I'm showing here for the full reservoir description, you can see that there is, I'm including that density also is constrained by gravity data, and CSEM data, control source electromagnetic data, would constrain resistivity, right? So this is a case where we are in an area where we have CSEM data likely a marine area or so. Okay, and so, well, then we'll include in the knowledge network this component. It depends on the area. The seismic part, I'm just using here seismic modeling. In the examples I show with the Monte Carlo, this was reflectivity. This was sawpits and convolving with a surf wavelet. But nothing in this theory and method is limiting that we can insert the full waveform inversion here. In my examples, it's not done because we are in some previous stage in full waveform inversion, but in future, the idea is that seismic modeling will be here on elastic full waveform inversion.
Okay. Our last question, how do you assess the application of neural networks for quantitative seismic interpretation? Are there neural nets-based methods which deliver comparable results to establish seismic inversion algorithms?
Well, I included neural networks in this description slide here for the different ways to solve inverse problems. In the way I see it, is another method to solve inverse problem. We may compare it with the optimization. In the optimization, we go step by step, linearize, go through Bayesian, try to go to the maximum a posteriori probability model realization configuration. In the neural network, because it is nonlinear, the estimation tries to go straight forward without iterations, okay? So you can say at the beginning, okay, it's much faster. It's only one step. Okay, but take care, but for being able to make this one-step nonlinear estimation, you need to do an important and large training of the network, which means that you are estimating many coefficients of the neurons and so on. So the inverse problem is done before. So there is a workload before, and there is an additional workload because to train the network, you need to generate the universe of training cases. And generating the universe of training cases, you also take a lot of work. So it's quite relative. I mean, in some problems, it can be better. In other problems, it might not be so promising. There is some sort of increased interest in neural networks, and it's justified because in some settings, very large computing software companies understand that neural networks are kind of generic to solve inverse problems, but in the generic way may be biased with what the universe of training is. It's not universal. You train the neural network with a given set of training models or realizations, and it is not going to work in another set. So I see this as an additional toolbox. That would be my answer. I think they are working very well for instance, estimating or picking horizons. So there are things going on, but I don't see them as the ultimate solution for everything.
All right. Thank you, Dr. Bosch. Thank all of you for attending the SEG Latin America Regional Advisory Committee's webinar as part of our webinar series, Recent Advances and the Road Ahead. Please look for our social media posts to register for more interesting talks. Thank you again for attending, and thank you, Miguel, for an interesting presentation. Until next time, have a great day, stay safe. Goodbye.
Okay, thank you very much to you, Laurie, and to all attendants. Goodbye.
Thank you.
Glad to answer any other question through my email or contacts. Bye-bye.
Thank you. Bye-bye.